Hi, I would like to talk about 1.6 differential form. Um, I would like to first define what the differential form is. I will not give a rigorous definition because we are not ready for complete definition yet. So uh, I will use the iteration given by the textbook, and I'm gonna explain something about this. So for a differential form, we can think from a one form because we already know what one form is. One form is just something like a linear combination of dy, dz, dx. So we can think dx, dy, dz here as something like a vector. So one form is just a linear combination. Then the we can think a differential form is a combination, but it can be from zero form to n forms. So if it's like a k form, then we will have we can think that it is something like a power. So if it is a three form, then we have a dx, dy, dz. So this definition is not very rigorous, but it's enough for us to understand this section. And next, we should know some operations. And the most important operation for differential form is a wedge multiplication. So we can use this to represent it. I want to specify a specific theorem, which is theorem 6.4. And there are some rules. The first rule is exactly the same thing what we have done in last section. So I will omit the first one, the proof of first one. And I want to talk about is the next one and the third one. So we can see here, what a phi, the second theorem is can be explained as a real value function times a differential form, which is exactly the differential of that real value function wedge product the differential form plus uh, the real value function itself and times the differential form, a differential of the phi, where phi is a differential form, and f is a real value function. So we will skip this because we can directly to prove 3 because a differential form will finally give us a real valued function, but it's a kind of like a complicated one. So if we can prove the third one, then we have the second one. So for this, we can set phi equals du, and we can use directly to use this because we do, it doesn't matter it doesn't matter to know anything else about it except du and dv, because we can find the representative to this. If we can show for this simple case, we can show for general case. So now we want to show the simple case. So now here is a we can think this is a star equation, and we will prove from another from this way. And so we have this, and the next is to prove this. So we can add this together, 1 and 2, and we see it is exactly the same as a star. So this theorem has been proved. Actually, we will not talk about very detail about the differential form, because it requires kind of topology stuff. So this is my presentation. Thank you.